The last type of proximity analysis I want to talk about is density. Density is where we map the highest and lowest concentrations of features, which is different than interpolation, where we're predicting the values between known points. Density calculates the quantity of something per unit area. For example, people per square miles, lightning strikes per acre, or businesses per square kilometer. Density surfaces are good for showing where point or line features are concentrated. And there are two general methods, point and kernel density. And if you look in the upper right-hand corner, you can see in the geoprocessing pane in the Spatial Analyst Tools toolbox, there's a density tool set with kernel, point, and line density geoprocessing tools. Now, the point density geoprocessing tool, also known as simple density, applies a 2D search area around each cell to calculate cell density. The search area can be circular, rectangular, donut-shaped, or wedge-shaped, and it's fitted over each cell. Individual cell values are calculated by dividing the number of features that fall within the search area by the size of the area. So in the example on the right, you can see that I have a search area of 2.88 acres. And within that search area around the cell for which I'm trying to calculate the density, there are 7 observations. So 7 divided by 2.88 equals 2.4 observations per acre. Now, the larger the search radius, the smoother the density surface you create. Now, I like point density because it's a simple density model in which not only can I run the geoprocess, but I could actually manually go in and confirm that I'm getting the results I expect because the math is really straightforward. Sometimes you need a more sophisticated density model like kernel density, which we use to apply not only a 2D search area around each cell, but also a 3D curved kernel over each point to calculate cell density. And so a circular area is fitted over each cell, and a smoothly curved bell with a base equal to the search area is fitted over each point. And so you can have sample points that fall outside your search area that still impact the density of the cell that you're trying to calculate. If you look at the example on the right, you can see that the sample point at the location gets a multiplier of 1, and then as you move out to the edge of the search radius of the bell, the multiplier falls to 0, and so it has less and less weight. And so individual cell values are calculated using the weighted point values within the search area by the size of the area. The larger the search area, the flatter the kernel. Kernel density also tends to be a little bit smoother than point density because of the impact of sample points that fall outside the search radius that still can affect the density calculation of individual cells within the search radius. In ArcGIS Pro, we use the Spatial Analyst and Image Analyst extensions to access a suite of tools for performing comprehensive raster-based spatial and image analysis. The Spatial Analyst and Image Analyst extensions include raster geoprocessing tools, functions, and workflows. We're most familiar with tools, where we are running a tool in our toolbox to generate an output data set. Raster functions are similar to geoprocessing tools, and they include a lot of the same processes, but the output is stored just in cache rather than creating a new data set. And so it really makes it easy to iterate through a bunch of raster functions till you get the result you want, and then you can export that out to your geodatabase. Raster workflows chain together a bunch of different geoprocesses to perform a larger analysis. So for example, raster workflows that you'll find on the analysis ribbon in the workflows group include suitability modeler and visibility analysis. Now, ArcGIS Spatial and Image Analyst supports raster data management, map algebra, which we'll talk about when we discuss raster overlay analysis, cost modeling, which we'll talk about when we discuss raster connectivity analysis, surface interpolation, terrain modeling, suitability modeling, which is what we're doing in our project, along with visibility analysis, and even image classification. Now, the additional geoprocessing functionality available in Spatial Analyst and Image Analyst extensions are in addition to the core ArcGIS Pro licensing product. And so they have to be licensed separately. And you can see if they're licensed in ArcGIS Pro by clicking on the Project tab and then the licensing section. And in the licensing section, you'll see which version of ArcGIS Pro you're using, Basic, Standard, or Advanced, and which ArcGIS Pro extensions you're authorized to use. And you can see in the example on this slide, I'm authorized for both Image Analyst and Spatial Analyst, as well as some other extensions. Now, we've already discussed geoprocessing in a previous topic, but when you are performing raster geoprocessing, it's very important that you have your environmental parameters set correctly. And it starts with the file names. Now, the file names are not really an official parameter, but as a general rule, you need to make sure that your raster data sets include 13 characters or less. Now, in a file geodatabase, a raster data set can have more than 13 characters and it can have spaces. But the problem is a lot of the underlying code that runs many of the raster geoprocesses is 30 years or older. And back then, you could not have really long file names or spaces or weird characters in your files. And you'll find that occasionally you'll get an error that's really difficult to track down, and it's because the file name is longer than 13 characters or has a space or a weird character in it. So make sure that your file names are 13 characters or less and that there's no spaces or non-standard characters. Now, if you open up the environments at the project level or at the tool level, you'll find that you can set the workspace. The workspace includes the current workspace, which is the default location for inputs and outputs, and the scratch, which is the default for temporary results. And again, I've learned over the years to apply some general rules when I'm creating a workspace. One, use lettered drives, not named drives, and short paths that don't have spaces or non-standard characters. A lot of times, again, you'll get an error in a geoprocess and you won't know why, and it's because the path is too long or it has a space in it. So a lot of times when I cannot figure out what the problem is and why my geoprocess keeps erroring out, then I'll put all my inputs in CTemp and I'll set my outputs to CTemp and run the process and see if the error is being generated by my workspace path. Some other environmental parameters that I set when I'm processing raster data, including my output coordinate system, which should be projected and the same as the inputs. My processing extent, which identifies the cells on which the process is performed. And the processing extent can only be a rectangle. So if I have a study area that's a rectangle, I'll often introduce that in my raster geoprocessing environment. So all my output is only for that study area. In the raster analysis geoprocessing environment section, you can set the cell size of your output raster. You can use a mask to identify cells on which the process is performed, which is the same as the processing extent, but unlike the processing extent, the mask can be any shape. You can also set the snap raster to align the lower left corner of raster output cells with the selected snap raster cells. So if you want to make sure that your input cells align with your output cells, then I'll go ahead and select a snap raster as well. Last, I'll often set the raster storage settings where I can set the pyramid settings, which are basically different resolution and zoom levels for my raster data set. I can calculate statistics automatically if I would like. I can use different compression algorithms for my data, set the tile size and how I'm going to resample my data, and last, how I'm going to process no data values. At this point, you should be able to explain how to measure cell and raster geometry. When we calculate geometry in a raster data set, it all ties back to the cell length, which is the X width or the Y height, and the cell size, which is the X width times the Y height. And then if you want to calculate an area of a collection of cells, you multiply the cell size times the cell count. You should be able to differentiate between global, local, focal, and zonal raster statistics. Global statistics are statistics for an entire raster data set. Local, or for a column of coincident cells between multiple rasters. Focal are statistics for a neighborhood around a cell, and zonal are raster statistics calculated for individual zones in a raster. You should be able to explain how to classify raster data sets utilizing symbology or reclassify raster values utilizing geoprocessing tools like reclassify. You should be able to compare and contrast deterministic and geostatistical interpolation. Deterministic predicts surfaces from measured points, and geostatistical predicts surfaces from random points compared to the statistical properties of measured points. You should be able to compare and contrast simple and kernel density analysis. Simple or point density is a really straightforward form of density where you have a search area and observations within that search area. And so you divide the number of observations by the search area to calculate the quantity of something per unit area. Kernel density is just a little bit more sophisticated process for calculating density in which the individual sample points are weighted with a kernel or a bell, which allows you to spread their influence over a larger area. And last, you'll use raster proximity tools to create resampled, generalized, interpolated, and density rasters both in the lecture demonstration and in the Onion Creek Trail Suitability Analysis project.